Hello and welcome in a new video. In this exercise, we are studying a case of a central force, which is the gravitational force that is acting between two masses. So let's start with this application. An artificial satellite with mass small m orbits around the Earth with mass capital M. So we have two masses. We have a satellite of mass small m that is orbiting around Earth. Okay, so the big circle is for Earth. It has a mass capital M, and the small mass is for the satellite. There's an approximately flat orbit centered on that of the Earth and located at an altitude h equal 800 kilometers. So the satellite is at a height h from the surface of the Earth. So h is between the surface of the Earth and the satellite small m. The Earth's radius is given as r equals 6,400 kilometers. So they gave us the radius of the Earth, and the acceleration due to gravity at the surface is g equal 10 meter per second squared. So here they precised that at the surface of the Earth, g is equal to 10 meter per second squared. Why? Because in fact, g changes with the altitude. But when you are near the surface of the Earth, we say that g is equal to 10 meter per second squared. Okay? So g depends on the altitude from the surface of the Earth. The question is to determine the orbital speed v of the satellite and its period t around Earth. So we need to find the orbital speed v of the satellite. This exercise is an application of the fundamental relation of dynamics or Newton's second law, in the case where we have one force, which is the gravitational force. Okay, so we will find v based on Newton's second law on the system. Which system to consider? We are studying the satellite, so our system is the satellite. And so let's start with the fundamental relation of dynamics. It states that F equal ma, and the only force acting on the satellite is the gravitational force Fg, and it's equal to ma. Okay, in this exercise we will use the normal and tangential accelerations because we have a circular motion. Okay, let's take it as a general rule. Whenever we have a circular motion, it's very convenient to use the normal and tangential accelerations because these normal and tangential accelerations will simplify our solving of the exercise. Okay, so A can be written as an plus at, and I remembered you what is the gravitational force. The gravitational force is equal to g times the capital M times small m over the distance between the two masses. So here the distance between the two masses is from the center of gravity of Earth to the center of gravity of the satellite. This distance is called small r, and this is equal to the radius of the Earth plus the altitude h. That's why I wrote that Fg is equal to g m times small m over the radius or the distance separating the two masses squared. So the distance separating the two masses is r plus h. Okay, now so they want us to find v. Well, how do we find v if we want to use Newton's second law? It's very simple because v is related to the normal acceleration, because we know that an is equal to v squared over r. we need to project this equation on the normal unit vector to find an, and from an we can deduce the orbital speed v. Okay, how do we draw en? En, in fact, is centripetal. It's directed toward the center of the circle, so it's directed toward the center of the Earth in this way. And we can draw E tau, the tangential unit vector, as following. It's a vector which is perpendicular to En, and it's directed in the direction of the motions. The projection of Fg on the normal will give Fg because the gravitational force is centripetal. It's directed toward the center of the Earth. So the projection of Fg on the normal will give G capital M small m over the distance squared equal M an. The projection of A on the normal direction will give us an, and an is equal to v squared over the distance separating the two masses, which is r plus h. From this equation, we can deduce the expression of v as a function of capital G, the universal constant, as a function also of capital M and the radius of Earth as well as the altitude. So we simplify with m and small m and r plus h of both sides, and we will obtain that v equal radical of gm over r plus h. Well, in this exercise, we know the value of r, we know the value of h, but we don't know the values for the universal constants and the mass of the Earth. So we need to find gm. It's simple to find the numerical value of g times n. How? Okay. Since we know that the only force acting on the satellite is its weight, then we can write that the gravitational force is equal to weight only at the surface of the Earth. So at the surface of the Earth, we can say that the gravitational force is equal to the weight of the satellite, and therefore we can write that the gravitational force G capital M small m over r plus h squared is equal to mg. So for h equals 0, and this corresponds to h, the altitude equal 0. So at h equals 0, this is 0, and we have g at h equals 0. We know g at h equals 0, it's equal to 10 meters per second squared. It's in the given. Okay, so g. So this is a very important remark. Please pay attention that g corresponds to an altitude that is very near to the surface of the Earth or on the surface of the Earth. Okay, so g is for h equals 0. And thus we can find the values of g times m. So g times m is equal to g small g r squared. Here small g is the acceleration due to gravity, whereas capital G is a universal constant that figures out in the expression of the gravitational force. Okay, we found what is g, the product of gm. Then we can find the speed, the orbital speed. So the orbital speed will be equal to radical of g or g0 r squared over r plus h. If we replace each term with its numerical value, so v is equal to r, capital R, the radius of the Earth, which is 6,400 kilometers. So kilometers means we have to multiply with 10 power 3. Radical of g0 is 10 meter per second squared. It's in the SI. And r plus h. So we have to make the addition of 6,400 plus 800 kilometers. This will give us 7,200 kilometers. Therefore, we have to multiply with 10 power 3 because the answer is in kilometers. And finally, I converted the answer to kilometers per second instead of meter per second because it's more convenient to use in this case a kilometer per second. It makes more sense. And finally, to find the period of rotation around the Earth, we use the definition of the period of rotation. It's equal to 2 pi over omega. Now, what is omega? Omega is the angular speed. How do we find the angular speed in the case of a circular motion? We know that V is equal to omega cross R. So V is equal to omega times R times sine of the angle between omega and R. So if we go back to our figure, omega is along K. It's pointing towards you because our rotation is like this. So omega is along K. Because omega is given by the direction of omega is given by the right hand rule. Since the rotation is in the counterclockwise direction, then omega will be pointing towards you. So this is the direction of omega. What is the direction of R? The direction of R is in this, like this. It's the radial direction. So omega and R are perpendicular to each other. The angle between them is 90 degrees. So if we go back to this expression, V is equal to omega times R times sine 90. And V is along E tau. Okay, so we can find that V, this is in fact to prove that V is equal to omega times R in the case of a circular motion. So omega is equal to V over R. So we substituted omega with V over the distance separating the two masses, which is R plus H. And we found that the period of rotation is equal to 2 pi times R plus H over radical of G R squared over R plus H. And we obtained finally that the period of rotation is equal to 1 hour 40 minutes.